All right, so there's some pre-notes before we kind of get into 7.1 to recall the things that we talked about. But in this units, we are going to be doing confidence interval and sample size. Sample size comes from what testing you need to do to figure out what kind of interval confidence you are. When we talk about confidence interval, we're talking about like, all right, I think it's going to be this. Like you're basically stating that, yes, I think the mean, the standard deviation, all of these things will be here, and I'm about 90% confident, or I'm 95% confident, or I'm 99% confident. The more confident you are, the smaller your information is because, or sorry, the more data you have, where it's like shrinking your data to be closer to where you want it. We're never 100% in statistics because there's always that little chance that we could be off. But 99% is pretty darn close. Use confidence of intervals mainly as statisticians to basically prove when a company hires you, they're like, hey, we want to test this product out and we want to put it in the market and we want to know, like with our sample space that we've used, and usually they'll use like 1,000 people they've given a sample to. And they'd be like, all right, after these samples, do you think that we could make a profit? And so you would do the math and they're like, hey, we want you to be 95 or 99% confident. So we do the math and to figure out if we are that confident. Now, with statistics, you never agree with it. You either agree with the null hypothesis, which is what we're going to be getting into, which basically the null hypothesis is not the event happening. So you agree with that, or you agree to fail the null hypothesis, but you're never agreeing with your actual hypothesis. Yes. We're talking about statistics, not facts. No. So statistics would be more or less, do you think this product can be sold somewhere? You're doing statistics on an event that has not happened yet. This is factual. There is a wall there. Who knows? That right there, I'm 99.9% confident it will be. But there is a liable that something could crash into the wall and the wall is no longer here, right? But again, we don't agree. We just fail to agree with the null hypothesis. So there's enough information to agree that I don't think the wall is going to fall, but I'm not going to agree saying the wall will be there. See how that kind of works? You never agree with what you want to happen. You either agree with the null or you fail to agree with the null. Which basically the null is just the null is basically the event not happening. Okay. Now, with that all said, depending on what kind of variables you have, how big your sample size is, what information is given, there are different type of tests that you operate on. Right. And so that's what we're going to kind of go through. We'll start off real basic with our normal distribution, and then we'll kind of go into what they call chi testing, double Z testing, Z left, Z rights, bimodal testing, all the different types. And then I think in y'all's little chart that you're allowed to use, I think most of those tests are there. However, you just need to know when to use each one. So given this information, I know I use this. Given this information, I know I use this to find out my answers. That's going to be what's hard about this. Right? So let's get into it. So that's a synopsis of chapter 7. So here we go. So inferential statistics uses a process of estimation, estimating the value of a parameter from data obtained from a sample. For instance, for each dollar you pay in county property tax, 22 cents covers the cost of incarcerated prisoners. That's in Pittsburgh. 8% of people surveyed in the United States said that they participate in skiing in the wintertime. That's another statistics. These results were obtained from data collected from samples of large populations. So these values are estimates of the true parameters. Remember, parameters would be the entire population, and statistics is the sample of the population. So basically, we can say 8%, but not everybody in the United States probably got surveyed. Just the people that answered the survey, 8% of them said they do go skiing, but might not be that. Like, for instance, I'll poll right now. Who goes skiing in the winter? Okay, so that's 1 out of 8 of us right now. So 1 out of 8 is, that means that 12.5% of the population must go skiing. So that's what we're inferencing. We're taking a sample and we're saying the parameter must be this. Go ahead. But you didn't agree with the vote when I voted. All right. So common assumptions must be met before valid conclusions can be made. Some of these assumptions are: the samples are randomly selected. Right? I didn't randomize this. I took a statistics class, right? I didn't go, all right, let me take a poll one, cluster it, or maybe stratify it. Maybe I take the 10th person, or maybe I at a convenience and I'm at a door and I'm just randomly grabbing kids that are interested, but it wasn't random, right? It needs to be randomly selected. The sample size must be at least 30, or the population must be normally distributed. Normally distributed is the bell curve. Okay, so yes, there must be at least 30 in your sample size, but if you are told it's normally distributed, the sample size does not matter. You can't, as long as the facts tell us it's normally distributed, then we don't get to make the fact that it's normally distributed. If it's told to us it's normally distributed, we won't know how many people are in the sample. Right? So you can use a histogram to see if it is approximately bell-shaped. And check for outliers. So just like in the last unit, if our sample is large enough, we could put a histogram or something and see if it's bell curve. For instance, the question on the test, would that have been normally distributed? No, it had 2 points that it went up, so it's actually binomial, or not bimobile, sorry, bimobile, right? Which, so therefore we wouldn't be able to use this, and then we would have to make sure the sample size was at least 30 to be able to figure out any of these statistics. All right. So this says 7.1, but technically it's combined with 7.2. But 7.1 and 7.2 is your 7.1. So when you're looking through your homework, 7.1 and 7.2 will be one thing. So in 7.1, the first half is talking about confidence intervals. So we're going to find the confidence interval for the mean when the standard deviation is known. So when the population standard deviation is known, this is the process for it. We also have a different process, and we'll talk about this tomorrow, when the standard deviation population is not known. Okay, so definition, confidence interval. What do you think these 2 blanks are going to be? No surprises here. So a confidence interval is a specific numerical value estimate of a parameter. Remember, parameter is the entire population. The best point estimate of the population mean. Population means the little sigma. And the sample mean, which is our Roman numeral with the line above it. All right, so the sample mean is used instead of the median or mode because means of samples vary less than other statistics when many samples are selected from the same population. Go ahead. Oh, that is the standard deviation. Best point of estimate of the population mean. I did. And the sample mean. Ooh. I wonder if they used the wrong one. It really is. Man, they used it throughout the entire process. So the best point estimate of the population mean that's I was like best point estimate of the population mean. Population standard deviation is the sample mean. Sample mean. Surely not. Google says population mean is the mu. That is the population standard deviation. That's why I looked it up is with confidence interval. All right. So just note that when we see this symbol all over this chapter, it is this. All right, here we go. So good estimators have the following properties. They're unbiased. So the expected value or the mean of the estimates obtained from the samples of a given size equal to the parameter being estimated. All right. Estimated. 2, they're consistent. For a consistent estimator, as sample size increases, the value of the estimator approaches the value of the parameter is estimated. So basically it just means that the larger the sample size, the closer that my information should be getting to the actual information, which makes sense because we looked at this as a limit as well. The third thing is they're relatively efficient estimators. So of all the statistics that can be used to estimate a parameter, this estimate has the smallest, probably error, smallest variance. Remember, variance talks about how spread out their data is. So if it's pretty small, their data is not, their data on all their means won't be spread out. All right. So in confidence intervals, statisticians prefer to use interval estimates because the sample means are somewhat different from the population mean due to sampling error. One of y'all's test questions. So definition, interval estimate. Can you guess what these blanks are going to be? All right, so an interval estimate of a parameter is an interval or a range of values used to estimate the parameter. The estimate may or may not contain the value of the parameter being estimated. So again, the estimate may or may not contain the value of the parameter being estimated. All right, so here it says a degree of confidence must be assigned before an interval estimate is made. This is a percentage starting how confident you want to be that the interval does contain the true population mean. The interval of 95% confidence is not as wide as the interval for 99% confidence. Basically, if you want to be 99% confident that the population mean is going to be there, this is how wide your range is. So this could be like 50, that's a 4. 50 to about 100. You think between 50 and 100, I'm 99% confident my interval, my mean's going to be there. If I want to be a little bit broader, I can be like, all right, well, 95 percentile, I think it's more like 70 to 90, right? So notice the smaller my confidence interval goes, the smaller my numbers can go, right? Tall roulette. But yeah, so same process. The more confident you want to be, the larger your parameters are going to be in hopes that it does fall there. The smaller your confidence level is, the smaller your parameters can be, because you're like, all right, if I am wrong, I wasn't like that specific, right? So if I wanted to be like 80% confident, right, I could be like, all right, well, this is like 75 to 80, right? And then if I'm wrong, well, there was a 20% chance I'd been wrong. So that's kind of why this is like this. So to increase the confidence that the true population mean is the interval may be wider, right? So the more confident you want to be, the wider your interval will be, and vice versa the other way. So the confidence level of an interval estimate of a parameter is the probability that the interval estimate will contain the parameter, assuming a large number of samples are selected and that the estimation process on the same parameter is repeated. Right? So basically, this little confidence interval is that's your probability that you think that the mean will fall somewhere in that ballpark. Right? All right. As you can guess, this right here is going to be confidence interval. So a confidence interval is a specific interval estimate of a parameter determined by using data attained from a sample and by using the specific confidence level of that estimate. So how do we get our confidence interval? Well, we have specific ways to do that. So yes. So we're not randomly just going to go, I'm about 90% sure the mean's between 0 and 1 million, right? Yeah. We can get a little bit more specific on our data depending on what our information is. We could technically save ourselves a lot of work. Your number is between 0 and 1 trillion, just so you know. Like I am 99% confident that's where it's at. But again, I didn't say 100 because it could fit like right over 1 trillion, right? which is like my luck. So, all right, here we go. So we keep going. It says that. I mean, technically, no. Everything happens because something was a variable had thrown that point into it. Yeah. I really don't, to be honest with you. Like, oh no, definitely run into the ditch to make sure that cat does not go fully in front of me to get back onto the road. And then if you run it over, it technically didn't finish running across, so the bad leg doesn't start. So, I mean, that's my okay. All right, here we go. So the interval estimate is based on the central limit theorem that we learned last unit. That states when the sample size is large, approximately 95% of the sample means of the sample size samples taken from a population will fall within plus or minus 1.96 standard deviations of the population mean. Remember, that was like your z-score. And this right here is the mu, which is our population mean, our correct sample, plus or minus 1.96 times the standard deviation of the population divided by the square root of the sample size. Again, this right here was a test question on your test. Remember that the z value that separates the middle 95% of the outer 5% is 2.5% on each end. We saw that as well. Like if we're doing 95% of our probability, we want to do 2.5 on each side of the normal distribution. Our critical values at plus or minus 1.96. So at that 2.5% on both sides, we saw that that was going to be a z-score of 1.96. Right? We did that math in the previous unit, and it's just bringing that back. So when a specific sample mean is chosen, there is a 95% probability that the interval is the population mean plus or minus 1.96 times the standard deviation population divided by the square root of the sample population size. Right? So that is basically what we can do is if we want to be that confident with our information, once we know our population mean, then we can say, hey, this is what it's going to be between, and we're this confident about it. And that's basically, again, you're basically stating that your sample mean that you're getting is going to fall between this range, given the population mean. And there is a 95% probability that the interval specified will be then the same formula. We just changed it out for the sample mean rather than the population mean, will contain the population mean. Right? It will be as long as we are dealing with 95% confidence. If that confidence changes and we talk about 90% or we talk about 99%, then we would have to go calculate what those z-scores on the end are. What was the question? You could. If you could just figure out what your mean score is on all test taking, and then you could go, all right, I'm confident I will make between a 82 and a 99 or whatever it is, whatever your population mean is. All right, we'll continue this discussion tomorrow.